A very warm good morning to all of you. You have had a very hectic course for spread over 2 weeks, and I'm sure most of you are now quite tired mentally. So, what I'm going to do today is not to load you further with more theory and more technical details, but my goal of this talk is to tell you a story. And the reason why I want to tell you a story is it's a very gripping story. And that story tells us about the times that we are in. And I'm going to begin by talking about the creation of Fortran, okay, which has been one of the most influential developments of computer science. So here is my challenge. I'm going to talk about challenges in compiling past, present, and future. And I'm going to talk about the biggest challenge, which was the birth of the compiler, how compilers came into existence. Then we'll talk about the structure of modern compilers, and then we'll talk about modern challenges. And then we will conclude the talk. So the reason I want to talk about the birth of the compilers, the creation of Fortran, is I believe it's been one of the most influential developments in computer science. We can't imagine what life would have been if that had not happened. So this story, it has all the elements of a compelling story, a real need, a community with a strong belief in the impossibility of the goals defined by the need, a bunch of people refusing to heed the common wisdom, and a risky proposition whose impact of failure is difficult to imagine, even after a century of its success. And I'm going to elaborate on all this in the rest of the talk. So all this culminated into a spectacular success, converting the skeptics into firm believers. There were people who didn't believe that some such thing is possible, and there were some others, courageous people, who made it possible. However, unlike fiction, this story is not the cliched feel-good victory of optimism over pessimism. It is a story of courage and creativity guided by pragmatic vision, creating a history. So this is what we want to see. Okay? While ease of programming was one of the main reasons for quick acceptance of Fortran, it became feasible only because of the optimizations that the compiler performed. In most cases, these optimizations systematically mimic the craft employed by gifted assembly language programmers. And this is the most important observation that we wish to think about. However, and this is more interesting, in some cases, they went far beyond. So much so that it was not easy to map the generated code to the source code, and some amount of effort was required to see that the two were actually semantically equivalent. Okay, the creation of Fortran and its compiler was a wonder because it successfully showed that expressiveness and efficiency of computation can be achieved together, and the ideas and practice created in the process remained unsurpassed for several decades. So that's roughly the background of the story that I want to tell you. Okay, so let's skip this question. Why is compiler construction a relevant subject? We talked about it. Let's go straight away to the birth of a compiler. So if you look at the pioneers of programming languages, you see that there have been several people who have been trying to define what we today know as a programming language. I mean, so I have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 20 efforts listed here on the screen. Okay, some of them were notable. For example, Plankalkul by Konrad Zuse, and Lanning and Ziller's effort, and Grace Hopper's effort. So the point is, there were many efforts, and yet a breakthrough had to wait for John Backus and his team. So the Fortran compiler was created by John Backus. The language was designed by John Backus and his team. So we need to go back into history to understand why was it so, and more importantly, we don't want to look at just the history for what it is, but also for the lessons that it has for us as we talk about compilers in the year 2021. So, in the era before the birth of compiler, computing was the best wording that I found described in the older documents was it was what is called the hand-to-hand combat with the machine. Just imagine yourself, now we are using computers in so many different ways. I am sitting here in Mumbai, you are sitting somewhere else, rest of the audience is spread over the entire country. But at one point of time, and I'm talking about 1945, 50, around that time, computing was a completely different ballgame. It was a black art. Just imagine yourself that in order to write a program or run a program, what you have to do is, first of all, you have to book a slot with a computer center. And you might get a slot at 12 o'clock in the night on Saturday. So you reach the computer center at 12 o'clock in the night. And then you are ushered into a room which is maybe 25 feet by 25 feet, huge room, and you have a huge big machine in front of you, and you start using the machine. Okay? So things that were available to you at that point of time was the problem that you wish to solve, the huge big machine consisting of relays, and they would emit a lot of power, the room will heat up, and cooling is required, and the manual of the computer, and your individual creativity. Programming languages didn't exist. You simply write in machine code. You wrote 101, the binary code. So people noted that computers were pretty crazy things. They had very primitive instructions and extremely bizarre input-output facility. So the celebrated example is what was called the Selective Sequence Electronic Calculator, or SSEC, which was used from 1948 to 1952. It has a memory of 150 words. Just imagine, we're talking about several GB of memory. I mean, my laptop has 4 GB of memory. Somebody has 8 GB of memory, gigabytes of memory, and here talking about just 150 words. Just imagine how the situation was. And it was constructed out of vacuum tubes and electromechanical relays. So, just as a story of what it meant to have to do a hand-to-hand combat with machine for writing programs, there's a story of paper tape. As you can see on the screen, there's a paper tape reader. So the idea at that time was that there was a punching machine. You punch your program, you type your program, and it gets punched into paper tape, and then you put this paper tape in a paper tape reader, which will read the program and load in the main memory. So that was the relation of the paper tape. So this paper tape was influenced by Jacquard's handloom, and that's why Jacquard is also considered an influential person in computer science. So the idea was to punch holes, and those holes would record whatever we wanted to write in the program. And then you would have a paper tape reader like this. So the story goes something like this. The programmers in one situation punched paper tape, glued it to form a paper loop, because the same thing was to be executed in the loop again and again. So they observed that there was a problem that appeared in one iteration of the loop, and then it would disappear, and then once again reappear. So this was very funny. If there's a problem, it should appear in every iteration of the loop. Why should it appear only in one iteration of the loop? And the pattern repeated many times. And I do not know how many of you know of Mobius strip. Can someone tell me if anyone knows about a Mobius strip? Is there anyone who has not heard about Mobius strip? If you've not heard about Mobius strip, then I have to give you a small demonstration. Can someone just speak out? Yes, there are some messages. Let me just pick out a scale before I show you what I want to show. Just let me get ready with this. Okay, so let me create a Mobius strip. Yeah. Okay, so what are the messages? What do the messages say? Is there a message? Hide. Oh, there doesn't seem to be a message. Okay, so raised a hand. Okay. Please, there are Venkat Kirti has raised hand. Mayur Dahibate has raised hand. So please unmute yourself and speak out.
Sir, we don't know about Mobius strip.
You don't know what
If you
Mobius
can
strip
show.
is. Okay. So let me switch on my camera. And are you able to see? I have a paper strip here in my hand. Are all of you able to see it?
Yes.
Yes, sir. Yes.
Okay, very good. Now let me show you what I mean by this. So let me draw a pattern. I need to take a pen and draw a pattern. So as you can see, on one side of the strip, there is some pattern, and on the other side of the strip, there is no pattern, right? So this paper strip has two sides. Now I can take and glue it like this. I can create something like this, in which case, as you can see, the outside has a pattern, but the inside doesn't have any pattern. Now, if by mistake, instead of gluing it like this, if I glue it like this, now we have a problem. Now we have a problem because we start saying that outside I have a pattern, outside I have a pattern, outside I have a pattern, and now we feel outside we don't have a pattern. Because the two surfaces have been interchanged. So a Mobius strip is a strip which doesn't have something called an outside and something called inside. I mean, I remember when we were in a college, we used to tease each other by asking a simple question. You hold a cup in the hand and you say on which side of the cup is the handle, and the person would say on the right side. Then you hold it in this side and then say on what side of the cup is the handle. Then you say it's left hand side. But the point is that there are surfaces which don't have inside and outside, and then you say, oh, the handle is on the outside. But then there are these surfaces like Mobius strips that don't have inside and outside. So the problem reappeared, problem disappeared and reappeared again because it became Mobius strip. So in alternative iterations, it was being read from different sides. And this is how, and just imagine how difficult would it be to debug a program. You thought there's a problem in the program, but the problem is in reading your program. And there's a famous remark. So this is something called debugging by the ear. So when IBM 70 defense calculator arrived, it didn't use so many mechanical relays. And then people said, how are we going to debug this enormous silent monster? The point is, programmers would hear some clanking noise, some noise, and they will think that maybe this is a problem. So by repeated occurrence of the same sound, they would try to find out what the problem was. But there is no sound. So how do you know what is the problem with your machine? I mean, when your mechanic looks at your car or a scooter, the mechanic could hear the sound and say, okay, maybe there is this problem. Imagine you putting your ear to your laptop or your computer and trying to imagine what kind of a bug your program may have. So that was the situation. So it was hand-to-hand combat with the machine. Okay. So yeah, I have to get back to my slides. So the beliefs of the times are in modern times, they would appear very crazy. So popular mechanics, very influential magazine, predicted in 1949 that computers of the future will be very light. They may weigh no more than 1.5 tons. So that was the prediction, that we are going to have very lightweight computers and maybe not more than 1.5 tons. And today when we buy laptop, we worry if it's 1.5 kg or 1.1 kg, and if it's 2 kg, we say, oh my God, it's very, very heavy. So ENIAC, which was completed in 1947, weighed almost 30 tons. So that's the kind of thing that you're talking about. You're talking about the weight of weight much more than the weight of your car. Okay, and the editor of Prentice Hall Business Book wrote in 1957, I have traveled the length and the breadth of this country and talked with the best people, and I can assure you that data processing is a fad that won't last out the year. He predicted that in 1957 that computing is a fad and it would cease to exist in the next year. And now we are in 2021. Okay, and there was some humor about programming in octal. So there's a standard joke: why can't programmers tell the difference between Christmas and New Year Eve? Because 25 in decimal is 31 in octal. And Grace Hopper wrote something very interesting. She said, we programmed it in octal, thinking I was still a mathematician. I taught myself to add, subtract, multiply, and even divide in octal. I was really good until the end of the month, and then my checkbook didn't balance. It stayed out of balance for 3 months until I got hold of my brother, who was a banker. After several evenings of work, he informed me that at intervals I had subtracted in octal, and I faced a major problem of living in two different worlds. And then Grace Hopper said that may have been one of the things that sent me to get rid of octal as far as possible. So just imagine, I mean, instead of writing 101 in binary, you're writing in octal, but you're still writing programs in octal. And people were really troubled by this, and they wanted to get rid of octal and they wanted to write programs in something better than that. So there's something called priesthood of computing. So the articles note that programming in the America of 1950s had a vital frontier enthusiasm, virtually untainted by either the scholarship or the stuffiness of academia. Okay, programmer inventors of early 1950s were too impatient to hold on to an idea. They won't try to develop that idea until it could be fully developed and a paper written. They wanted to convince others. Action, progress, and outdoing one's rivals were more important than mere authorship of a paper. An idea was the property of anyone who could use it, and the scholarly practice of noting references to sources and related work was almost universally unknown or unpracticed. And this was something that was very bad about computing. There was this priesthood, there were influential people who would want to keep ordinary people out of the access to computer. And this story seems to be a story of all civilizations. In our own civilization, we have had priests who would not let ordinary people understand Sanskrit or the books in Sanskrit. So priesthood wanted to preserve the order because their importance lied in lots of people not knowing what they were doing. So priesthood wanted and got simple mechanical aids for the clerical drudgery which burdened them. So these priesthood were so-called mavericks or inventive people or geniuses who would try to do things that appear magical with a computer and most other people won't be able to do, because they regarded with hostility and derision more ambitious plans to make programming accessible to a larger population. To them, it was obviously a foolish and arrogant dream to imagine that any mechanical process could possibly perform the mysterious feats of invention required to write an efficient program. So they believed that they were great, and it was their creativity and inventiveness that made programming possible. They refused to imagine that you could write programs more systematically. Remember, when I say write programs, it refers to writing programs in octal, not writing programs the way we write programs. And then there were also the purveyors of snake oil. Because when there is a problem, there will be lots of people who will say we have a solution without they actually having the solution. So the documents note that the energetic public relation efforts of some visionaries spread the word that their automatic programming systems had almost human abilities to understand the language and the needs of the user. Note the word automatic programming. The word automatic programming came into existence because the belief was that writing programming means writing in octal, and you could have a system which will write the program in octal for you. So the word compiler didn't exist at that point of time. It was an automatic programming system. The compiler, as we know today, was imagined as a system to which you give some specification, and the system will write programs for you automatically without you helping it. And that is why it was called automatic programming system. Okay? So some people said that they already had automatic programming systems, whereas closer inspection of these same systems would often reveal a complex, exception-ridden performer of clerical tasks, which was both difficult to use and inefficient. Okay, so such was the situation. And then came into existence what we call A2 compiler. Compiler word was first coined by Grace Hopper. So programmers had a library of subroutines. Now, if you realize the word of library, why we use libraries in our programs. Where did the word come from? The word came from a library of subroutines. So what it meant, there actually was a room with shelves on it, on which we used to have card decks for performing specific operations. So if somebody wanted to do an operation, what somebody had to do was to go to that room, pick up that deck of cards, put that deck of cards with his or her own program. So people would say, I got this from the library. So there was actually physical collection of cards related to common services required in programming. And that's why people called it library, because it was like a library of books. You borrow a book, read it and put it back. Similarly, you borrow a deck of cards from that room and put it back. And that's how the word library came into existence, which we use until today. Okay. So they needed to copy the subroutine on the coding sheets by hand and change addresses manually. So what Grace Hopper did was, instead of copying things, she added a call operation whereby machine would copy the code and update the addresses. So that library would have certain addresses, but when you load it into your program, it would get loaded at some other place, and the addresses would have to be changed. And programmers had to physically change those addresses in their programs. So Grace Hopper added this call operation, which is what is a call of a procedure. And the machine would automatically read those deck of cards and would change, update the addresses based on where those cards were being read. Okay, and the name of compiler was used because it put together a set of subroutines. It compiled together. What is compiling? Compiling in English means putting things together. And that's why Grace Hopper called it a compiler, a term which we use even now. Before that, it was called an automatic programming system. Of course, there were some real high-level languages also. In Konrad Zuse's Plankakul language, he developed it in a small village in Germany in 1945. It was called program calculus. There was only design, there was no implementation, because computers were destroyed by World War II. He didn't have access to physical machines. So he simply designed the language. And there was this language called Whirlwind at MIT. It was fully algebraic in terms of supporting expressions, but it was very, very inefficient. So what was the challenge for creation of high-level languages? So what people now call as a tyranny of exclusive or. Do you go for expressiveness or do you go for efficiency? So Konrad Zuse's language was very expressive, Whirlwind was expressive, but it was not efficient. And you want to compare, you want the execution efficiency to be comparable to the things that people wrote in assembly language. Grace Hopper's A2 compiler was actually an assembler. So now instead of octal, people are writing in assembly because there are names given to instructions, and they could write very efficient programs. If you have a system, why would people accept that system if it didn't generate a program which was comparable in performance to the manually written programs? So expressiveness meant giving higher level abstractions. So it basically increased the efficiency of a programmer in writing a program, but it lowered the efficiency of execution of the machine. So expressiveness meant supporting features that were not supported by the hardware. And in most cases, most time was spent in floating point subroutines. Machines, whatever machines we had, didn't have floating point computations directly. And not much attention was paid to address calculation and good use of registers of the machine. IBM 704, when it came, it directly supported fast floating point operations. So now you had, for the first time, a piece of hardware that would support the floating point operations. And the need of expressiveness vanished, because now you don't have to carefully write things for floating point operations. They were already supported. And that revealed several inefficiencies. And these inefficiencies were clumsy treatment of loops, indexing as in what we call as arrays. They were called indexed variables. So A of 1, A of 2. So in accessing array elements and references to registers were the sources of inefficiencies. And this is what led to rejection of automatic programming. People said, oh, the system can't really generate a program as good as I can write manually. And therefore, people were not interested in automatic programming. So the genius of John Backus lies in the following observations. He realized that the main reason of inefficiency was a clumsy treatment of loops and array address calculations. He felt that if that could be handled, things may be far different. And the possibility made a lot of economic sense, because machines were becoming cheaper and manual effort was becoming costlier and costlier, because writing programs wasn't really very easy. It was a black art and very few people could write programs. And then he realized that language implementation was far more critical than language design. And we will come back to this point in the last part of our talk. Okay. The word Tran in Fortran conveys the spirit, translation rather than design of a language. The language didn't matter. Fortran was formula translation. So the genesis of Fortran lied in the following. The motivation was programming and debugging cost had already exceeded the cost of running a program. And as computers became faster and cheaper, this imbalance would become more and more intolerable. And so John Backus set up the following goals. Can a machine translate a sufficiently rich mathematical language into a sufficiently economical program at a sufficiently low cost to make the whole affair feasible? So effectively, you're talking about a compiler generating a good program, supporting a rich expressive language, and the compilation itself is very fast. The generated programs needed to be comparable to hand-coded programs for efficiency. Okay, so how did they design the system? So John Backus notes that we simply made up the language as we went along. We did not regard design as a difficult problem, merely a simple prelude to the real problem, designing a compiler that could produce efficient programs. We had notions of assignment statements, subscripted variables, what we call as arrays today, and the do statements as the main features. Whatever else was needed emerged as we tried to build a way of programming on these basic ideas. So how did they go about compiler design? They use simple things that people use even today. Study the inner loops to find out most efficient method of execution. Find out how efficient code can be generated for sample statements. Even now, when we have to write an optimizer, I mean, I've been having some discussions with a company called carrier, they have their own language, and they want to write a compiler. And the first thing that I said was, show me examples of source program and the generated program. Show me how the manually written program can be more efficient. So find out how efficient, what is the efficient code that you would want for sample statements. And then we generalize the observations by removing specificities and exceptions. So this is something that John Backus and his team used way back in 1953. So effectively, they raised the level of computing from number processing to processing text that processed numbers. So before John Backus, everyone was writing programs to process numbers. John Backus thought that we could write a program that could process a text, and this text would process the numbers. And this is one of the things that I keep telling my compiler students, that your tagline should be that other people write programs to process data. We write programs that process programs to process data. So we are at one level higher than all other programmers. So Fortran project was approved in January 1954 and the system delivered in 1957. So Backus initially promised to the IBM management that he will deliver the project by 6 months, but the IBM management gave him a lot of freedom. It was a very supportive management. Every 6 months, Backus's manager would drop in the room and say, where is the compiler? And he will say, okay, come after 6 months, and then he will go back. Once again, he will pop in and ask, where is the compiler? And Backus would say, we need more time. The usual story. And it was a very young, energetic, enthusiastic, and inexperienced team. So this inexperience is something that helped them a lot, because all experienced people knew that compilers can't be written. They were absolutely convinced, and they wanted to maintain that priesthood. But these were a bunch of young, inexperienced people who didn't know the impossibility of what they wanted to achieve, and therefore they wanted to achieve it. And they had a great team spirit and synergy because they all shared a common dream. And John Backus notes that the best part was the uncertainty and excitement of waiting to see what kind of an object code all that work was finally going to produce. It was a great sport in those days to scan the object program and either marvel at the translator or question its sanity. So in some cases, it would produce wonderful program, wonderful piece of code fragment, which people couldn't imagine before. And in some cases, it produced such a stupid code that they wondered whether what they're doing was really worth the effort. Okay, so their inexperience helped in ignoring the doubters and overcome discouragement and despair.